All right, here we've got some notes on solving polynomials from factored form. Now, you should have this handout in front of you, and we're going to go through it together. So it says here, solving in factored form, and then we've got this right here. Similar to our quadratic function, we'll be able to find the solutions to polynomial functions from factored form. So if you think back to our previous unit, where we solved quadratic functions, and one of the methods was solved by factoring. Well, we're going to use the same method here to solve polynomial functions. And I'll just give you a quick reminder of what that looked like. So if we were able to factor a quadratic, and it always gave us two factors, x plus or minus some number. I'll just make up a number here. There's one factor and a second factor. These factors are always binomials. So there it is, two factors, and we would need that equal to 0. So this here would be our quadratic equation in factored form, equal to 0. And then how did we solve this equation? How did we find the solutions? From here, it was pretty easy. We just did x equals, and then we changed the sign. So because this is a plus 2, our solution is going to be x equals negative 2. And then over here, because this one is minus 5, our solution is going to be x equals positive 5. And these here were our two solutions. Okay, now let's say, for example, we have a polynomial, a degree 3 polynomial. Something that we talked about before, and we're going to go over again in these notes, is that the degree of a polynomial is always equal to the number of factors that it has. So in factored form, a degree 3 polynomial might possibly look like this. We'll just add one more factor, x minus 4. So here we've got 3 factors in factored form. This was a degree 3 polynomial. It's equal to 0, and each factor gives us a solution. So we've already got these two, x equals 5, x equals negative 2. And here we would have one more solution, x equals, change the sign, positive 4. So here for this degree 3, we get 3 solutions. That's kind of where we're going with this, okay? Okay, I'll clear that out. If you didn't have to write that down. If you did, that's okay. I just wanted to kind of show you that here at the very beginning. So let's go ahead and fill in some stuff here. It says here the solutions of a polynomial are the points at which the polynomial's graph intersects the x-axis. All right, so fill this in here, solutions and intersects. And you know what? This is also something that we talked about with quadratics. If you guys remember, the solutions were equal to the x-intercepts. So here's another thing. You don't have to write this down. I just want to show you here. Right? This is kind of convenient. Look, we've got a little graph of a quadratic. Here's the x-axis. How many x-intercepts does it have? 2. Those are the two solutions. Right? Whatever the x value is for this x-intercept, that's a solution. Whatever the x value is for here, that's another solution. It's going to be the same thing for polynomials. So here's a graph of a polynomial. And let's take a look. How many x-intercepts does it have? 1, 2, 3. This graph has 3 x-intercepts. It's going to have 3 solutions, and they're just going to match up with the x value of the x-intercept. So whatever value those are with the x value, those are the solutions. Okay. A couple more vocabulary words to fill in here. It says solutions are also referred to as zeros and roots. So this is just giving us some extra vocabulary words. These words all mean the same thing. The word solution and the word zero and the word roots, you could use those interchangeably. They all mean the same thing. If we got three words that mean the same thing, this means this is something important, right? We already understand this. Solutions to an equation are very important. So there's a couple different names that we can use to call solutions. Okay, let's keep going here. The fundamental theorem of algebra. It says here an nth degree polynomial function will have exactly n number of solutions. And again, those solutions, we could call them solutions or zeros or roots. So this is just a general way of saying this. This is not giving us a specific degree. This is just saying n. So n could be any number. N could be 3, degree 3. N could be 7, a degree 7. N could be 100, a degree 100 polynomial. Whatever the degree is, it's going to have the same number of solutions. That's what this is telling us here, the fundamental theorem of algebra. And over here, this is just an example. Look, a degree 5 polynomial is going to have 5 solutions. The degree always matches with the number of factors, and the factors always match with the solutions. So there it is. Okay, a couple more things to fill in here. Solutions are just x-intercepts, or where the y value is 0. And that's why we call them zeros. Why we call the solutions 0 is because they're at the x-intercepts and the y value is always equal to 0 at that point. Therefore, we want the x value where f of x is equal to 0. And this is important, right? We want to get our equation. F of x is whatever equation we have, a degree 3 polynomial, degree 5, whatever it is, we need it equal to 0. Just like we did when we were solving quadratics, we had to get the equation equal to 0 first, and then we could factor. All right, so here's some steps for solving. Rearrange the equation by canceling until the equation equals 0. That's the first step. We need it equals 0. So whatever you have, usually we have all our terms on the left side and then equals 0. And if it doesn't start off equaling 0, then you have to cancel stuff out. You got to do some algebra moves, add or subtract terms to get them moved over to the other side. Of course, we'll do some examples so you'll get to see that. All right, step 2, factor. Okay, factor. Okay, and hey, look, here's a little asterisk here. This is telling us we're going to use synthetic division to check for a factor, and then once we find a factor using synthetic division, that's going to give us a new polynomial that drops by a degree. Okay, and what we're going to want to do here is reduce our polynomial, reduce the degree of the polynomial until we get a quadratic. Remember, quadratic is a degree 2. So we're going to do synthetic division as many times as we need to until we have a degree 2. And then once we have a degree 2 quadratic, then we have a method for factoring the quadratic, which is bottoms up. Okay, step 3, set each binomial equal to 0 and solve for the x-intercept, aka the solution. A lot of times, if it could be just as simple as changing the sign. If my binomial looks like this, x minus 3, my solution is going to be x equals, change the sign to a positive 3. But if the binomial, maybe if the binomial looks like this, maybe it's 2x minus 3 is one of the binomial factors. Then, to get the solution, this is what I have to do. Set it equal to 0. So 2x minus 3 equals 0, and do some algebra moves to solve that for x. So I would do this, plus 3 to both sides, so that the 3 cancels out there. And then we would get here 2x is equal to 0 plus 3 is a 3. And then we would go one more step, divide by 2 on both sides. So the 2 cancels out, and this would be the solution. So this binomial, 2x minus 3, would give us a solution of x equals 3 over 2. You could just leave it like a fraction like that, or you could write down the decimal equivalent. Okay, so I just wanted to show you that here. That's what step 3 is saying. Step 4, double check. You must have the same number of solutions as the function's degree. So when you get to the end, this is something you're going to check, right? Is the number of solutions that we found equal to the degree of the polynomial? That's what it is. Example 1, we'll do this here in just a moment, but take a look. To start off, this is a degree 3. So I already know from the beginning I need to get 3 solutions. Once I have 3 solutions, then I'm done with that, solving that equation there. Okay. Okay, let's go ahead and do the first example here. The directions tell us to find all solutions for each polynomial, then use Desmos to sketch the graph. Okay. So on our first equation here, this is what we got. Here's the equation, and this is a degree 3. 3 is our biggest exponent. So that means we should expect to find 3 factors, which is going to give us 3 solutions here to this equation. And then when we graph it, we should expect to see 3 x-intercepts. All right, let's go ahead and get started now. What does this tell us here? Rearrange the equation until it equals 0. So notice, look, here's the equal sign. We got 2 sides, the left side and the right side. This equation is not equal to 0. What we're going to want to do is get it equal to 0. And to do that, we got to cancel out these terms. We got to basically cancel those out and move them over to the other side so that it's equal to 0. Okay, so that's going to be our first thing to do here. So to cancel out this term, this is a minus 26x. We're just going to do the opposite. We're going to add 26x. To cancel out this plus 16, we're going to do the opposite of addition, which is subtraction, minus 16. Now, whatever we do to one side of the equation, we got to do to the other side. So I got to do these same 2 things, plus 26x and minus 16, on the other side of the equation. I'm just going to write them here. If I had like terms that they would combine with, I'd try to line them up. But as we'll see here, there are no like terms, so none of the terms will combine. So this is what happens. This cancels out. This cancels out. So what we have here is going to be equals 0. That's what we want. Now over here on the left side of the equation, we want to check if there's like terms. Like terms are going to have the same exponent. And guess what? None of these terms do. This is exponent 3, exponent 2. This is an x to the power 1. The invisible exponent, if you don't see it, is a 1. And then this term is a constant term. It doesn't even have an x. So none of those terms will combine. This is what it's going to look like. We're just going to write them out in standard form. So I'll write biggest exponent first, then minus 11x squared, then plus 26x, and then minus 16. So now we have the equation equals 0. And now we can take a look at step 2 here, which is factor. All right, we're going to factor. Now notice that this problem, it's actually giving us one of the solutions already. Now in the future, not too long from now, we're going to learn some methods to kind of find these on our own, or to find potential solutions that we're going to check. But for now, we're given one. It tells us x equals 2 is a 0. Or in other words, x equals 2 is a solution. Remember, those mean the same thing. What I do want to make sure that we understand here is that this means we're going to have a factor. So we're going to have a binomial factor of this polynomial, and it's going to look like this. The sign is going to change. So if x equals positive 2 is a solution, then x minus 2 is a factor. Okay, just so we're aware of that. Now, the way we're going to factor this guy, this is a degree 3, we have to use synthetic division. Okay, we're going to divide this polynomial by x minus 2 using synthetic division, and this is what it's going to look like. So the number that goes out here, our k value, is going to be this number, change the sign, or this original number, don't change the sign. Okay, either way, it's going to be a positive 2. That's going to be our k value, positive 2. And then I like to do this. I like to label my columns x cubed, x squared, x constant term. Let's fill in the coefficients. 1, negative 11, 26, negative 16. And let's go ahead and do synthetic division. So take a look what we get here. We get a remainder of 0. That's what we were expecting to get because we were already told that this is a solution, means this is a factor, means we should get a 0. And that's what we got. All right, now we're going to take what we've got down here. So this gives us the answer to the division. When we divide the degree 3 by the binomial, we get this here. These are the coefficients of the answer. Remember, the degree drops by 1. So up here was x cubed. This is going to be x squared, x constant term. Let's put that together and just write it over here. So we're going to get 1x squared minus 9x plus 8. Okay, and now what we want to do is factor this guy. This is a quadratic, so we can factor it like so. A value is a 1, B is a negative 9, C is an 8. So the two numbers that are going to multiply to make a positive 8 and add to make a negative 9 are going to be negative 1 and negative 8. Okay, so this is going to give us two more factors here, x minus 1, and then from here, x minus 8. Okay, and now what we've got is this. We've got all the three factors. Remember, we have a degree 3, so we were expecting to find 3 solutions. That also means we're going to find 3 factors. We have them. This is the first one that it gave us, plus these 2 that we found. So I'm going to write these down. I'm running out of space, but I'm just going to write it down here. So here's our original equation in factored form. X minus 2, x minus 1, x minus 8. Okay, and remember, look, we had this equals 0. So we have this equation equals 0. The solutions, right, Step 3 here, set each binomial equal to 0. That's what we're on here. But when you have a binomial like this and there's no coefficient in front of the x, finding your solutions is as simple as changing the sign. So we're going to do this. X equals, change the sign to a positive 2. That's a solution. And we already knew that. They told us that up there. X equals 2 is a solution. Then we get another solution here. X equals positive 1. We get another solution here. X equals positive 8. Okay, those are the solutions. So we solved it here. Let's put a box around these. That's our final answer for the solutions. Now let's sketch a graph. And, we can already start to plot some key features. Knowing these solutions, these are also going to give us our x-intercepts. So let's see. Okay, all of these x-intercepts are positive. So maybe I'll put my x-axis right here. Let's see if this gives us enough space. Excuse me, this is our y-axis here, and then I'll put our x-axis here. And let's see here. 1, 2, 3, 4, 5, 6, 7, 8. So we have an x-intercept at 8, and then also at 1 and at 2. Okay. And we can take a look at Desmos to get the rest of the information. Really, we just want to know the end behavior of this graph. We haven't yet talked about end behavior, but we will soon. Basically, what it means is the graph going up or down on the far left-hand side and the far right-hand side. Let's jump over to Desmos and take a look at the graph. All right, here's Desmos. Now, you know what I'm going to do here? Let's do this. Not only will we check the graph, but we're also going to check our answer and see if it's right. We can do this by inputting to Desmos the original function in standard form. So I'm going to use, just so you know what we're doing here, this version of the equation right here that we had equal to 0. I'm going to input that. That's our standard form. X cubed minus 11x squared plus 26x minus 16. Okay, we can start to see a graph there. In just a second, we'll make it full screen. Now, the second one that we'll enter in here on the next line is going to be factored form. So these are the binomials, x minus 2, x minus 1, x minus 8. Okay, let's take a look. Hey, how many graphs do you see here? I'm only seeing one. I see this blue graph, but I know that over here we've got 2 equations typed in. Now, if I turn off the blue graph, guess what? There's the red graph. So our blue graph lays exactly on top of the red graph so that when I turn it on, the red one disappears. That means these 2 equations are identical. They're the exact same equation, just in different forms. The first one is standard form. The second one is factored form. Hey, by the way, if you happen to make a mistake and you got this wrong, let me just change a number here. Change the 8 to a 9. Hey, now take a look. The red graph and the blue graph, they don't match exactly. So that means we didn't get it right. This is where we have to go back and check our work. Okay, but when I change this back to an 8, we can see it's a perfect fit. Okay. Now look, these x-intercepts we already plotted these. These are our solutions 1 and 2 and 8. And notice that the graph is going down on the left side. It comes and it curves through the x-intercepts and it goes up on the right side. Let's see, what's the y-intercept at? Negative 16. Okay. We might be able to fit that on here. 1, 2, 3, 4. Let's do this. We'll scale our y-axis by 4s. So we'll go negative 4, negative 8, negative 12. Here's negative 16. That's where we saw on Desmos we have our y-intercept And let's just go ahead and connect these now with the smooth curve. Looks like that. Of course, this graph is not exact. It's not perfect. It's a sketch, but we do have the correct x-intercepts and y-intercept, and the graph is going down on the left and up on the right like it's supposed to. Okay, that's number one.